The MOSFET, or metal oxide semiconductor field effect transistor, is the building block of computers, but they sound like something straight out of science fiction. Fortunately, once you break them down into the parts that they are made of, they become much easier to understand. A MOSFET acts as a switch with two states, on and off. An on state has a low resistance and lets current pass. The off state acts as an open circuit, so no current flows. But how does it actually do this? A MOSFET usually has four parts: the N-type regions, the P-type region, and the gate. The N and P regions are named after the charge of what carries a current through the material. Both are made of a mix of silicon and another element. Which element you use determines whether it's N or P-type. Phosphorus can squeeze into silicon structure, but it has an extra electron that it can't share with any neighbors. This extra electron can move more freely throughout the material than the ones shared between neighboring atoms. Because electrons are negatively charged, a phosphorus-filled region is called an N-type region. Boron can also fit into the silicon lattice, but it has a missing electron. This gap acts like a positive charge that moves opposite to electrons. This is why the boron-filled region is called the P-type region. When the MOSFET is off, the extra electrons and gaps diffuse between the P and N region border through a process called recombination. As a result, the phosphorus and boron atoms that lost them now either have more protons than electrons or more electrons than protons. They hold a charge opposite the carrier they lost. Phosphorus will become positive while boron will become negative. These ions will repel anything trying to get past. This is where the gate comes in. The gate is a big plate that doesn't quite touch the P and N-type regions but comes really close. It uses a positive charge to pull the negative electrons in the N regions towards the gate and push the gaps in the P-type away. This forms a sort of bridge made of the extra electrons that lets current flow freely between N-type regions. How does this device even make a computer, though? Let's look at what's happening around the MOSFET if we arrange it like this. If the MOSFET is on, then current prefers the path to ground, a point where there's the biggest difference in voltage, but not to the output. If the MOSFET is off, then current will have no choice but to flow through the output. The node is not the input into the MOSFET. We can arrange these MOSFETs to make more logic gates. When you have two NOTs in series, the output is always on unless input A and input B are on. It's not what input A and B are, a NAND gate. Similarly, you can put them in parallel, so that if input A or input B are on, then output is off. It's not whether input A or B are on, a NOR gate. There are many other logic gates, but all can be made with just a combination of NAND and NOR gates. You may know that computers run on binary. This is because the gates that they are made of use ones and zeros to communicate, on and off. Binary is, quite literally, machine language. It's incredible how simple parts like MOSFETs can make something so much more complex.